Okay.
And I'm here with,
there.
everyone knows, Doug Ford of Doug Ford Analog Design. And he's got some cool light panels for us because he's into everything lighting, right?
Including, everything analog plus LED lighting and stuff.
And you're the acoustic and audio guru.
Something a bit like that.
Awesome. So, yeah, look, we've got some panels. These are they're 1200 millimeters by 300 millimeters.
Nominal power, 60 watts input. Nominal output, about 3000 lumens. So nominal efficacy, around about 50 lumen per watt.
50 lumen per watt.
And unfortunately, that's around about what you can expect from these diffused flat panel emitters.
Yep.
The LEDs inside them are probably 120 lumen per watt. But by the time you go through the side emission process and diffusion, relatively low efficacy, but very good quality of light with low glare.
Excellent. That's exactly what I want. The idea is put these on the wall in front of me to light up my face in front of the video because the corner of the lab is actually quite dark. So that's the idea. So these are a strip of
strips of LEDs.
LEDs down the side.
Yeah.
Right. So there'll be a flat PCB down the side of that.
Yes.
We've got 4 inputs.
They've basically segregated the power to these into 4 groups, probably because they have 4 600mm PCBs.
Okay, and there's none on the top and the bottom? It's just
I don't
on the
believe
side?
so. Yeah.
Right.
And we can find that out quite readily by powering up one of the 4 groups.
Let's do it. We haven't powered this thing up yet, so...
Yeah, we have
we'll
here
give it
a 3 amp power supply.
Yep.
We have a controller, which is actually an RF controller for dimming.
And it comes with a little wanky remote control.
Ta-da!
So you can dim them from a distance.
So we'll put batteries in that later and find out how well it dims. Okay, let's run up.
Let's do it. Hey, here we go. We're up.
Okay. Now, depending on how well the video camera shows this,
it may not. I've got auto contrast,
this half.
auto exposure.
Yeah.
So, yep, we can see that.
Let's see
it's split in the middle there.
Yes. Now, you can tell that despite the fact that we've only got one half of it illuminated, its diffusion is really very good.
The diffusion is very good. It's well, we could get the light meter out and see what the difference is here as it drops going across, I guess. So we could almost get the function of the plastic.
If they've got it right, we'll be going from 100% to 50% to 25% over the span there.
And it's linear?
It should be linear per unit length, which actually makes it logarithmic when you plot it.
Right, got it.
So okay, that's the second half.
Yep.
No, let's run. Let's see if we can pick this half to illuminate. Let's see if we can get it right. No. Okay, let's try that one. Hey!
There we go. And that is really very even. I like that. That's impressive.
So if we get the next 2 up.
And that's not hard on the eyes at all.
No. When you have a large emitting surface like that, 3000 lumens coming out of a large surface like that represents really quite low glare. When you have 3000 lumens coming out of a tiny little point source, such as you can from some of the higher powered LEDs these days, it's a horrible amount of glare.
There we go. I've ramped it up a bit. It's not easy to capture such a bright source on a camera with background at the same time.
Do I look beautiful?
You look wonderful.
Oh,
your hair's a bit messy though. It's got that, crazy professional.
Windswept and interesting.
Windswept and interesting. All right. So that looks really quite nice. But they flicker down at the low end, do they?
That's what I've seen on the tests I did.
Yep.
But we'll re-verify it.
Excellent.
Any flicker will simply be due to the PWM frequency getting too low and starting to get into the visual range of 60 hertz, 50 hertz, 40 hertz.
Yep. And it might show up on camera depending on the frequency as well. We might not see it, but it might show up. Yeah, okay. Exactly.
We'll try that.
Because I'm shooting this at 25 frames per second. Well, that's 50.
Let's see if we can get some big frequencies happening.
Interesting. So there we let's switch them off and have a close look at the back of them.
Yep. Which actually won't reveal all that much.
Oh, okay.
But we might also pull out the chalkboard and sketch up the principle of operation of panels like these.
Is there a brand?
Yes, these come from QL LED.
QL LED in
Shenzhen.
In Shenzhen.
Yep.
And there's the four. There's the four cables running out. Just a standard DC 2.5 millimeter, 5.5 millimeter. Yep, DC barrel.
Also comes with fastening hardware that goes in there so that you can link them onto the roof.
Oh no, we can't see the LED. I thought we could see the board in there. Okay, no, they're just side attachment points.
That's right.
Right, okay. Got it. And how much do these things cost?
Well, they're at a price which will allow me to sell them locally for just below $200.
Awesome.
At this size anyway.
Right.
But
have you tried any other one hung low ones from?
Not in flat panel emitters.
Right.
I've got an unfortunate amount of experience now with LED fluoro tube replacements.
Which we're going to look at as well.
Yes.
We've got a whole bunch of stuff here, folks. We've got LED fluoro replacement tubes, and we've got these massive long ones.
Which are locally manufactured.
Locally manufactured by
Me.
Doug Ford and Log Design. Peter's over here too. Hey.
Okay,
right.
chalkboard time.
Chalkboard time. Chalk? So antiquated. We have evolved somewhat.
I haven't, I'm a Luddite.
Fair call. All right, Dougie, we're going to explain some of these lights, are we?
Yeah, so for those of you who aren't familiar with how flat panel LED lights work, you start off with a PCB loaded with bucket loads of little LEDs. Typically 50-50 package or 35-35 or thereabouts. Okay, you then have a large slab of thick acrylic. It might be 10 millimetres, 8 millimetres thick or thereabouts.
Just standard acrylic? Standard diffused acrylic?
No, actually standard
doesn't
clear
clear
acrylic. The clearer it is, the better. Because what you're relying on is light. Hang on, chuck us another colour.
Got plenty of colours.
Light from the LED entering here. As long as that angle is less than the critical angle, it'll undergo total internal reflection and total internal reflection, and it'll actually act rather like a fibre optic.
Does that mean you need a narrow angle LED, lens LED?
I will come to that because that is one of the areas of loss. If your angle of entry is too steep, you get external reflection.
Yep.
So the light doesn't enter in the first place. If the angle is shallow enough to enter, it might still simply refract straight out there without travelling. You'll also undergo some degree of diffusion in here, which is why some of this light will tend to reflect a bit like that, simply due to surface irregularities, so you will get some emission here. You'll be reinforcing all of that with, on the back side of it, a layer of white reflective paper.
Is silver mirror better?
Yes, but you want to avoid specular reflections. You actually want diffuse reflections, which is why you use white rather than silvered.
Right, even though that's greater loss.
No, because you can get white surfaces which have got about 99.5, 99.9% reflectivity.
Ooh.
It's just that when you do get a ray bouncing off them, instead of it reflecting, it will diffuse.
Got it. And does that have to be totally flush with the surface?
No, there can be an airspace. That side of it's not too critical. The other thing that you want on this face here is either a diffusion layer, or sometimes that diffusion layer is actually etched into that surface of the perspex.
So that's the key, a thin diffusion layer instead of diffused plastic.
Yes.
Aha.
So you want highly conductive, highly optically transparent acrylic, so that you can get your light over to near the centre without too much loss, but you still want it to diffuse so that you're not seeing the immediate glare from emitted from around here.
Yep.
And that's pretty much it. So your losses are this entry angle. Now, incidentally, I understand that 3M have, and probably others, have a film which you can place.
I was going to say, is there some magic gunk you can...
There is some magic gunk. Haven't tried it, haven't tested it, don't totally know its properties, but is reputed to basically get more of the light from the lead utilised within the acrylic. The other magic gunk is the high reflectivity film here. There's a few manufacturers of that around the place and more every day. And there are a number of plastics manufacturers, I think the Bayer, one of them, who are getting into this material with the right characteristics on the front face for good diffusion.
Got it.
But bottom line is, it's lossy as hell. Even with the best will in the world, the transparency of the acrylic is finite.
But that's what you, if you want a thin, diffused light panel, this is pretty much the only way to do it. I mean, ultimately, would it be better to have your LED here and shine out if thickness wasn't an issue?
Indeed. The other way of doing it, which does yield you higher efficacy but higher manufacture cost, is a dirty great big flat PCB plastered all over with LEDs, and somewhere over here in front of it a diffusion layer, so that all the light emitted by these tends to give you a fairly good homogeneous light output.
But I am imagining that wouldn't be as diffused as this solution, because you would still probably see the point sources still, maybe, as hotspots.
You can. If you get the diffusion layer too close to the LEDs, you start seeing the individual LED hotspots.
Or you can gook it with some magic gunk, perhaps.
There are magic gunks. One type of magic gunk I've seen is a set of films. Typically, you would also see these used on the LCD screens of laptops.
Oh, got it. Yep.
Which laptops tend to use just either a single CCFL tube or sometimes arrays of LEDs, and they need a high degree of diffusion.
They do. So, you get consumers complaining about hotspots, and because that used to be the case on the old notebooks. You get the hotspots on the edges where the
and colour shifts, etc., etc. It's an expensive solution, though. Doing that. The cheap, expensive solution is to use a simple diffuser, space it relatively far away from the LEDs, and just plaster this with many, many LEDs as closely packed as you can. You do tend to wind up with, first of all, panels which aren't as robust as this. This is solid. This is solid. If you squeeze it, you can't feel any flex. There's no give. You can actually drive nails through that and nobody cares, and it still keeps on working. And, if you want to, we can try that.
No thanks.
I have seriously seen nails driven through these, and they just keep on working.
Of course.
Can't do that with this. It's going to flex. Unless you have pillars in there to space that away, they're not as robust.
And in theory, you could make this panel flexible as well. In theory, if you use flex PCB and...
you would have to have a gel type acrylic, which you can do with a semi-polymerised PMMA.
Oh, okay.
But I wouldn't like to try it myself.
Right.
That's an experiment for others to perform.
Excellent. And we talked about the graph of the response, of the light response across here. What's that going to look like?
Ideally, what you'd want is if you're getting 100% here, at some point you're going to get 50%. Okay, now that 50%
where it is, we don't know.
And if that whatever length that is, in the same length, you're going to go from 50% to 25%. In the same length, you're going to go from 25 to 12%. So, in effect, it's a inverse square law relationship. Ideally, if you've got a second batch of those over there,
which we do in these panels,
you'd want to plan that half attenuation distance.
Yep.
So that the next one that you put over
They
here
cross in the
is
centre.
just about there,
Yep.
and they approximately cross in the centre.
Yep.
And that will give you an approximately even light across there.
So me seeing a hot spot in the middle is probably imaginary. It must be. By theory, it must be down.
Not necessarily. Not necessarily,
think so?
because if it so happens that on this stuff the 50% mark is there and there, then you'll actually get an overall brightness profile like that across it.
Ah, of course.
It won't be like that.
Yep.
So it won't be peaky.
Right.
It's just going to be vaguely brighter in the middle. Or if it's the opposite, it's going to be vaguely duller in the middle.
Yep.
It's not going to be extreme. Oh, except for edge effects where you might get a huge increase in brightness.
Of course, yeah.
Over at the edges due to edge effects around here.
We don't seem, with these panels, we don't seem to be getting a huge amount of that.
No.
Seems good for a one hung low brand panel.
Yeah. They've done their homework.
Yep.
The efficacy is around about what you'd expect of such a thing. I have seen flat panels quoted at up to 70 lumen per watt, but that would probably be for a horrible actinic dead 6,500K colour temperature with so much blue it burns your retinas out.
And these are, what, 4,000?
Yeah, these ones are 4,000.
These are 4,000, so they match my strip fluoros I put in here recently.
What most people are finding is that 4,000K is pretty much the ideal colour temperature for office lighting, task lighting, paperwork, electronics work, that kind of thing. For domestic lighting, anywhere between 2,700K and 3,500K, with most people seeming to have a vague preference for around 3,000K.
Okay, interesting. And where do the 6,500, you know, those huge daylight ones, those 6,500, 7,000 even?
Yes. You use those where you just don't care about the quality of light. You just want quantity of light.
Yep, got it.
Street lighting tends to be a little bit that way.
Right.
Car park lighting, particularly subterranean car parks and outside your local clubs, the car park out there.
So you get the greatest efficacy at around 6.5K?
Yeah, and the reason for that, where's a rubber?
Rub it.
Or an eraser even.
Sorry, we can't do the chalkboard.
Okay, let's do a plot of wavelength versus intensity.
Yep.
LEDs are based on a blue LED, which has got a spectrum a bit like that.
Yep.
And you chuck that into a phosphor. The phosphor gives you your lower wavelengths. Now, depending on the shape, on the balance of blue light versus phosphor emitted light, and of course the characteristics of the phosphor will emit light down here in the visible region, or if they've got a good phosphor, it might be a little bit down further towards the red.
Right.
Whenever you have a look at the characteristics of LEDs, you'll always see that characteristic like that, and it's the balance between the blue spike and what happens down here that gives you your colour temperature. Now, a cool LED will give you, well, actually pretty much what I've drawn there. Big blue spike and maybe that. A warmie will give you...
A warmie being about 3,000?
Yeah. Will give you relatively low blue in comparison with your lower spectrums.
Yep.
Now, there's also a characteristic of LEDs called the R9 coefficient. A lot of the phosphors don't have much of the true deep red output. The R9 parameter tells you how much true deep red you get, because a lot of the phosphors only really give you from your reddy orange through to your aquas.
Got it.
Incidentally, that point there, the saddleback, is usually just at aqua.
Right.
And for some reason, well, actually, we know why most leads are a little bit deficient in aqua, but your eye tends just not to notice it because it's picked up on either side by the blue of the lead itself and the phosphor emissions immediately that side.
Got it. And you're doing work on underwater LEDs too. Are there any tricks to underwater LEDs?
Apart from the mechanical construction of doing underwater luminaires or underwater electronics of any kind, I think the basic thing to recognise about LEDs or light underwater is that the blues are attenuated much more quickly, but they're attenuated primarily by scattering. And
got it.
Let's go for the...
Let's rub it again. More theory, folks. This is all off the cuff. We have no idea what we're doing here.
I've got no bloody idea what I'm talking about most of the time. If we're looking down on a swimming pool and we've got a light over here,
yep.
If that light is emitting red light, most of that red light is going to travel really well through the pool, but you don't get to see it. Why? Because it's travelling through the water, it lights up the wall over here perfectly nicely, but that doesn't give you a lot to see. The blue, on the other hand, fascinating.
Do tell.
It attenuates relatively quickly. It might only go, I don't know, maybe 10 metres would be the 50% point.
Right.
But all of that blue is scattering. It's not just being attenuated, it's scattering, and the pool iridesces blue, and it's a beautiful sight to behold.
Why do they scatter? Why does blue scatter?
It's probably got something to do with the size of water molecules,
or chlorine or something. Maybe maybe it's different between salt water and chlorine.
No.
No?
Nope.
No? Okay.
And
so
it doesn't matter whether it's fresh water or salt water, although I have seen learned studies which show the transmission of light through waters of different seas, and they do have different properties, but the differences aren't gross.
Right. So maybe the physicists out there can jump on to the forum and tell us all about it. Why?
Yeah. Bottom line is, blue light in a swimming pool looks beautiful because the whole pool appears to glow blue.
Brilliant.
Whereas red
no
light,
pun intended.
Whereas red light in a pool transmits just fine, but doesn't look any good. In order to make the redness of the pool equal to the blueness of the pool, you've got to really pile on the red light. You've got to have a lot of red light. And of course, you do run the risk, like blues and greens in a pool look inviting. I don't think that anybody wants to dive into a yellow pool or a red pool. No, we won't go there.
Let's not go there. Oh boy.
Okay.
And what happens to these panels when they age? Or you haven't got good data on that yet?
We've only got 4 years of data, and
only. What do you mean? These one hung low panels last 4 years?
Oh no, I'm talking about the underwater lights.
Underwater lights, right?
Yeah. So I've been in the business for 4 years doing the underwater lights for a local company, Aquaquip, and we've got 4 years of data. Failures are incredibly rare. It's delightful. The only real forms of failure they've had are if the luminaire leaks.
Yep.
And they had a couple that did that.
Do you seal them with a re-enterable potting compound?
No.
No, you just don't bother? You just rely on the O-ring seals and be done with it?
Yeah, in fact, these are now, they're basically glue sealed.
Oh, okay.
Because there's no need to service them.
Yep.
They either work or they're dead.
Yep.
One of the other reasons for them being dead is installers who forget that these are supposed to be low voltage lighting, run from 12 volts AC. We have definitely had a few that have had 240 volts put into them. The smoke has come out of the components.
The magic smoke, yep. Oh, boy.
Mind you, on the upside, we actually do have designed these such that the first thing that the power hits is basically fused protection, series fused protection, and parallel voltage clamping.
Right.
So when that does happen, there's basically a weak link that blows. You know, in effect, they're fused. So the potential for destruction, explosive destruction within it is small.
Got it.
And it means that nobody's going to get electrocuted diving into a pool that some wally has wired up. Just as an aside, Queensland has recently passed laws stating that you have to be a qualified sparky to do work on certain aspects of swimming pool lighting.
Even if they're 12 volts?
Even if they're 12 volts. Anything that requires, anything that doesn't simply plug together a logical sequence that is impossible to cock up, anything that requires a screwdriver or joining of wires, it needs a qualified sparky. Doesn't matter whether it's the 12 volt side or the 240 volt side.
Got it.
It has to be blindingly obvious to cretins how it goes together, or else you have to be a qualified sparky.
That's Queensland for you.
Yeah. Well,
beautiful one day, crazy the next.
Yeah, I was about to say, look, maybe they've got a high proportion of cretins. I don't know what the reasons for the laws are.
Hi to all my Queensland viewers.
Yeah. I do not respond to emails. It wasn't me, it was somebody else.
And what happens to these lights when they age? Do they just reduce in intensity and the spectrum stays the same?
Yes. The third form of failure that we've discovered is chemical contamination of the LEDs.
Oh,
now,
okay.
We kicked off using Cree XRE LEDs, which are actually more subject, I think, to chemical contamination than most of the current crop of LEDs.
Why is that? Physical?
Yes, it's their physical manner of construction.
Got it.
And we don't know if... and we actually sent these LEDs back to Cree for examination. They weren't able to tell us what it was.
All right.
And they did put them through their labs. All they could do is shrug their shoulders and say, well, yeah, it's chemical contamination. But here's the interesting thing. We suspect that it might be ingress of some form of chlorine vapour.
Oh.
And the LEDs are susceptible to things like chlorine vapour, various volatile organic compounds,
So
solvents.
you see this on the underwater LEDs, not the regular shop ones?
Correct. Mind you, we've also seen them in the regular shop ones where they've been operated next to stockpiles of pool chlorine.
Oh, there you go.
And what happens is the dyes on the LEDs go dark.
Right.
Not only low emissivity, but the actual dye looks discoloured and ugly.
So you can physically see the wear on them?
Yeah.
The contamination?
Yes, and the output drops to a tenth, a 50th of what it used to be.
Wow.
You can resuscitate them.
Do tell.
You operate them at very high temperatures, like 85 to 100 C on the dye, for about a fortnight, 3 weeks, a month. They come good again.
Do you have to do it on the dye? Do you have to light them up, or you can just put them in a thermal oven and bake them?
You could probably bake them, but we did it the easy way. We used self-eating.
Yeah, got it.
They're not fit for resale or anything, but the fact that you can revive them from chemical contamination is absolutely fascinating.
That is fascinating. So how did you know the dye temperature? You measured the back temperature and then you know the thermal conductivity of the...
We know what the thermal conductivities are. We know the input power to the LED. So hang on.
Let's
down to the drawing board.
Okay, down to the whiteboard again. Here we go.
If you've got a LED sitting on a heatsink, you know what the thermal resistance is from the lead dye to its solder junction point.
You do, because that's in the data sheet.
You can measure what the thermal resistance is from the junction point to the heatsink fins, because you can get a thermocouple on that, you can get a thermocouple on that, measure the difference in temperature, you know how much power you're putting in, and the maths is easy. So, bottom line is, if you put enough power into this to get the heatsink up to, say, 85 degrees C, and you know that you've got, say, well, I'll pluck some numbers out of the air.
Make it easy.
10 degrees per watt there and maybe another 5 degrees per watt there, total of 15. If you put a watt into that, and it's enough to get the heatsink up to 85,
Math
then
is easy.
you're looking at 100 on the chip.
Yep. Simple. I've done a video on that. LED lighting. Geez, that was a couple of years ago now.
Yep.
They're still going. The LEDs on my deck.
Yep.
Lighting up.
Yeah, we're not talking about high-level calculus and integration.
No, it's pretty dumb stuff.
Yeah.
It's a series resistance, Ohm's law type thing.
Yeah.
Yeah. Power is current, and the thermal resistance is the resistance, and the temperature is the voltage.
Yeah.
There's the electrical parallel there. No pun intended.
Too easy. Alrighty.
And that's all we need to know about LEDs. That's LEDs 101.
For the moment, yep.
Brilliant. Thanks, Dougie.
So, with a little bit of luck,
Let's check out the RF remote on these panels. Sorry, but we're gaining here.
that is fading down.
Yeah.
Now, apparently we didn't quite start with both of them at full bore.
No.
Can you see a little bit of residual flicker on the left one?
I can see flicker on the camera here.
These linear ones here
Yep.
have no ripple, so they won't be responsible for any strobing.
Yep.
They're PWM controlled, so
Got it.
but
Yep.
we don't know what PWM frequency they're running from.
So none of the ones we installed up in the ceiling here are PWM at all.
No.
They're all constant current.
Yes.
Right.
But any of your fluoros
Yep.
will have 100 hertz ripple.
They will. There you go. And we are recording this at 25 frames per second.
Okay, now let's see if... Okay, that looks as though they're both up full now.
All right.
Now, it might also make a difference on where the
There we
actual controller boxes are.
Yeah, it may.
Who
All
knows?
right. So
Okay,
let's
so fading down
fading down,
and down and down and down.
down and
You've
down.
actually got a pretty good control range. The fact that you can get them down to...
Yeah, that's pretty impressive.
Yeah. Now, visually...
I've got this camera set to fixed exposure, by the way, so...
Come on. Okay, that's as low as they'll go.
Yep.
And coming up. And that looks like pretty much full bore.
Yeah, I'm seeing no strobing at full brightness here on the LCD screen of the camera, but when it was halfway, I was seeing significant strobing.
When it's at 100% and 0%, there will be no flicker content because the PWM is either going to be full bore
on.
100% or nil. But yeah, as soon as you start fading a bit, you should start getting some strobing there.
Yeah, getting some strobing now.
Yeah.
I'm not sure if this will show up on camera, folks, but...
Bucket loads of light.
Oh, that's really sweet. I like it. Not bad for a one hello cheapie.
Yeah.
And these are 60 watt,
Yes.
rated 60 watt output.
Yes.
Got it.
No, rated 60 watt input.
It's input, sorry, yes, of course.
3000 lumen.
3000 lumen output.
Yeah.
What's a regular office fluoro in lumens?
Call it 70 lumens per watt for plain vanilla tubes. You might get 90 lumens per watt for a quad phosphor.
Yeah, which is what I got. Yeah.
And some of the new quad phosphor T5 tubes, which can only be run with electronic ballast, they're the very, very skinny ones.
Oh, yeah.
They can get in excess of 100 lumens per watt, but don't put your money on them.
Right.
And the other thing about fluoro tubes of any type, of course, is that their efficacy varies hugely with temperature, which is why you get the warm-up effect that we noted before.
Yep.
And which is also why at low temperatures, below 15 degrees, 10 degrees Celsius, quite often when they first spark up, they're half as bright as a dead glowworm. And they perform incredibly badly in sub-zero temperatures.
There you go.
LEDs rule.
Yep. None of this compact fluoro rubbish, right?
Well, compact fluoros are just a variant on the fluorescent theme.
Yeah, yeah.
They serve their purpose as a stopgap solution between incandescents and LEDs. Look, you'll see them around for half a dozen more years, but LEDs will take over.
Definitely. Oh, I think
As long as
within
the
a decade,
prices of
definitely.
LEDs
Exactly.
Yeah. And we're starting to see more and more solutions using LEDs that don't necessarily conform to your usual bayonet socket plug-it-in type lamps.
Yep.
There's still definitely a place for bayonet socket plug-it-in lamps because there's billions of such lamp bases in the planet.
Exactly.
But new lighting can use different form factors like these ones, which aren't just a slot-in replacement, they're a new lamp unto themselves. These strips up here, they're a new lamp unto themselves.
I can see these going into, these flat panel ones going into all the McMansions, because they look pretty jazzy.
Particularly if they're in 3000K colour temperature.
Right.
Which is it's the preferred colour for domestic applications because it's fairly close to that you would get from an incandescent lamp anyway.